so much for the kind invitation, and it's great to be here with such great names sharing this fantastic workshop. The outline of this talk is to talk a little bit about the need for learning and reasoning in the context of NeuroSymbolic AI. We typically talk about a cycle where some symbolic knowledge is translated or mapped into a neural network, which can be trained with data in the usual way, and then extracted. A revised knowledge is extracted to explain what has been happening, and that can be consolidated and then transferred to other applications. And in this process, we hope to do learning and reasoning in such neural networks. So I'll then talk about a semantic framework that seeks to contain many different approaches for such neurosymbolic learning and reasoning, and then move on to some of the limits of reasoning in neural networks and what I see as relevant directions going forward. So I don't need to tell you too much about the need for learning and reasoning following a talk by Leslie Valiant. I'm just adding a picture here to his very relevant robust logics paper. And just to say that learning and reasoning in the context of neurosymbolic integration is something that has been part of the objective from the beginning, from the late 90s. But differently from Valiant, I am concerned about ChatGPT and what has been happening recently, and errors of reasoning that can take place in such deep learning methods, which make the task of making sense of those errors and improving such systems with accountability urgent, in my view. And I think that Gary Marcus, when he gives a talk in this workshop later this week, I think he will certainly refer to that. And this has been discussed extensively in the AI debate that Gary chaired only last month. So this semantic framework that I'm going to talk about looks at, if you look at the paper, this is work with Simon Odense that we just put out also last month. The networks that are displayed in the paper are very simple, and I will focus on those simple networks. But that doesn't mean to say that these are irrelevant to the more complex models and the transformers and the convolutional networks and the LSTMs that are being used in practice now. So I'll try to create a connection between these simple networks and the more complex models. When we talk about a semantic framework, we are referring to connecting the stable models in a neural network, the stable states of a neural network. So if you run a neural network and it converges to a stable state with the models of a logical theory. So you can think of this as the local minima corresponding to models of a logical theory. And in this process, the network dynamics is implementing the fixed point computation of the logic theory in parallel. And this is the simple idea of creating this connection between stable states of the network. So the state of the network doesn't change, even though these are real numbers in the network. So we will have intervals there. The state of the network doesn't change after a while, and that corresponds to the models of the theory. And what is interesting in this paper here is that we show that many different approaches, they follow this same structure. So we have to go back, sticking with simple networks, to K-band and the CILP system going back to the end of the last century. And to give you an example of what we mean by this relationship between rules or the logic and the neural network. So in K-band, you have rules like these where which are mapped into a tree structure. And the goal of K-band was to perform learning with background knowledge. And if I'm not mistaken, this was the first system to add background knowledge into a neural network that was then trained from examples. And the goal was to improve the performance of the training given such prior knowledge. When we look at CLP, which followed, you have logic programming rules, and these are mapped into a network that has a single hidden layer, but that has feedback connections. So I can provide inputs to these neurons, and these are interpretations of the logic program, and they are propagated and then feed back into the input until there's no change. And as I said, no change means that whatever defines a neuron as being active corresponds to the literal in the logic program being true. And when we do this in the CLP system, we are concerned about learning and reasoning in the neural model. And in particular, we are interested in providing a proof of soundness of this translation to make sure that if a neuron is active in the neural network, then it is true in the logic program and vice versa. So this proof of soundness seems to indicate when we then apply this network to learning from examples, seems to indicate that we can get a better performance. So if we have a proof of correctness of the translation, so there are different ways in which different types of knowledge can be translated into network architectures, but we would argue that this proof of soundness is what is going to guarantee that hopefully there will be an improvement in performance if this knowledge is relevant to the task. And this is what we see in practice when we compare these approaches. And notice that the use of negation here makes the system non-monotonic, right? So what is not true is assumed to be false. So this is negation by failure. So we then started to ask the question, what happens if we try to extend this language and derive, consider more expressive representations? And in this book with Lamb and Gabay, we looked at some examples such as the muddy children example, the muddy children puzzle, where we now have agents, or the children here, and their knowledge at time t1, t2, t3. And that corresponds to connectionist modal logic. So we can solve the muddy children puzzle by having this kind of representation. And if we have time, we can go a bit deeper into how this happens. But at time t1, it's common knowledge that at least one of the children is muddy. At time t2, that at least two of them are muddy. And at time t3, that they must all be muddy. They don't know that at time t1. And the reasoning progresses by propagation of activations from these networks. And it's interesting that up to that level of expressiveness, we can show that proof of soundness. And this corresponds to modal logics being robustly decidable, as shown by Vardy in his famous paper. So we have this limit, and we would like to go beyond that to first order logic, which then becomes a challenge. And I'll talk a little bit about that challenge. But it's interesting that we can get these proofs of soundness up to connectionist modal logic. And we also want to find out how this can be useful in the context of more complex networks. So in my mind, and there's a lot of recent work on this idea of adding hard and soft constraints on top of deep networks. So as a layer, which performs reasoning on top of those networks. So this is where this becomes relevant also in connection with getting to the right level of abstraction as we do this. So we may accept that a complex network here is going to continue to be a black box. It receives some input, it does some object recognition and some pattern matching, but then there is a layer that could be a CILP layer, or it could be simpler. It could be a restricted Boltzmann machine. I'll mention that in a minute. And then there is an output as a constraint on the existing network. When it comes to a real application here in collaboration with Fujitsu, we've been looking at a CNN, for which it's quite clear where we want that knowledge layer or knowledge extraction to be, and it's in the fully connected layer here. So in this application, the inputs are X-ray images. There's a classification of that as either pure effusion or healthy X-ray, and we hope to extract, by looking at one specific layer, such logic programs. So these are pretty much like the ones we've seen before, with A, B's, and C's in the case of K-band and CILP. And here denoting negation with minus here and with this dash. And this logic program, what is interesting here is that by focusing on that layer, we can extract a pretty compact program that really shows that a lot of the kernels in the network are irrelevant when it comes to the description of what this network is doing, although they may be important when new data comes in and some new images emerge, of course. But here we can specify what this complex network is doing with high fidelity. So these rules represent pretty much what the network is doing in its classification. And in this paper here, the goal is to attach some meaning to these literals, right? What is CL or PA or not array and so on. So with this idea that, okay, we may have a reasoning layer, as it were, that sits on top of a more complex network, I think it's also important to go beyond backpropagation. Maybe there is too much of a focus on backpropagation. And in this paper with Son Tran, we look at RBMs, restricted Boltzmann machines, where you simply have an input layer and a hidden layer. And information, of course, goes up and down here. So if you want to relate this to what we have here, you can see that, you know, we go from input to a hidden layer, and this output could be also here in the input, right? So it's an input at the level of interpretations and a hidden layer. So with an RBM, we ignore that hidden layer that was needed before. And we show that we can actually use now contrastive divergence and represent propositional logic, which goes beyond the logic programs we were seeing before, because those didn't have this junction in the head. And now we can represent A or B in this way. And what I think is interesting here is that you have this input layer and hidden layer. We have some connections that specify constraints in propositional logic, and you can transfer some of these to a new target domain, right? So what we're showing here is an example where some of these connections are transferred to another RBM, others are left free to be trained, and we hope to improve performance when moving, let's say, from handwritten digits to characters, or in the previous application, when moving, for instance, from pure effusion to COVID X-rays. And the importance of such knowledge, I think, is really highlighted when we consider such transfer learning tasks, in which we hope to be able to build up that knowledge and reuse it, and therefore learn from less, as was mentioned before. Again, when it comes to concept learning and transfer learning, it's very important to consider how these concepts persist from one application to another, not just how knowledge may be transferred, learned in one domain and then reused, But here we start to go towards first order logic, and we look at, for instance, the concept of an object being larger than another object. So you may learn that from images of, you can't quite see this, but here we have towers of blocks, and you may learn that one tower is larger than another. How do we transfer this now to a more abstract domain, where by understanding the concept of larger than, we hope to apply it to, for instance, well, MNIST digit 5 is larger than 4 and 3 and so on, and therefore adding such consistency and constraints such as, well, it cannot be larger and smaller at the same time, and this concept of consistency, which is logical consistency across domains, I think is also very important, and this was the focus of this paper, which looked at autoencoders, and here again there is a critical layer to focus on, the bottleneck layer as the relevant layer to consider in this case. So we have such proofs of soundness up to connectionist modal logic, but not going beyond there. And we would like to handle actually full first order logic, certainly as our knowledge representation language. And in that case, with the use of logic tensor networks, what we do is not to map the logic into the architecture of the network, but to map the logic into the loss function. And so here you have the idea that you regularize learning with first order logic, or a variation, real logic that we use, which has small differences, but essentially the language is that of full first order logic, with an interpretation that is many valued, so either Lukasiewicz or Gödel and so on, from fuzzy logics. And so here now satisfiability is learning, so there's no proof of soundness, at least for now, and so this makes it different, but still fitting the semantic framework that I mentioned. So here we may not have the reasoning mechanism defined as precisely as in the case of the previous examples, because there we could guarantee that the computation was going to be equivalent, the computation of the network was going to be equivalent to the fixed point computation of the semantics. Here we are approximating, and all we can do is offer some measure of the reasoning capability of this approach. So if we look at this example here of LTN, we have some examples of X being of class A, so these dots, red dots here, some examples of Y being of class B, and we want to say that, well, if it's A, then it's not B. So this goes into the loss function. I'm learning a neural network that will create some kind of boundary here, but of course, without guarantees. And the next important thing, I think, in this space is to indeed provide such error guarantees, as was also mentioned by Valiant in his robust logics approach. What we have looked into, however, here is the idea of LTN plus XAI, which I'm referring to here, the idea of combining logic tensor networks with explainability and taking advantage of that NeuroSymbolic cycle that I mentioned to achieve modularity. So some of the knowledge in a module and some of the knowledge in another module that I can try and check for its reasoning capabilities that I'm happy with, and then make sense of all of this, or put it together, or reuse it. So if I query these neural networks and extract some symbolic description and representation for it, then I can obtain all the guarantees that we can get from that symbolic description. And that becomes my representation of that module of the logic tensor network. So this is the idea of extracting or querying these modules for symbolic knowledge. So all of that falls into the semantic framework that I mentioned at the beginning, But there is exciting and interesting work looking at proof theory as well. And there I include reduction to logic circuits, the concept and idea of soft unification, and of course SAT solving. In this paper here, we look at some examples of SAT solving using RBMs. So that is interesting, but we're not quite there yet. So the NeuroSymbolic approaches, I don't think they can match the symbolic approaches that were referred to by Vardy at the beginning of his talk. But this is an interesting future development. In terms of next steps, there will be events that were already mentioned by Alex Gray, the NESI workshop there. And we are seeing many different approaches and hybrid systems being proposed with different forms of representation, which I think is very valuable and important, but with a loose formalization of reasoning. And I think there we need to become more specific. We need to be able to say, well, this network or hybrid system is implementing a specific fixed point computation or resolution, or we could provide clear definitions of reasoning. So that's my point number 4 there. And in the meantime, we also have been kind of working towards a killer app, and perhaps it's large language models with common sense reasoning on top of it. And this will be discussed as a NESI challenge in the NESI workshop in the summer. So we are trying to create a proper specification of those tasks as a community. And we also need some benchmarks, what McCarthy used to call Drosophila examples, for us to consider. And multimodal coherent learning and reasoning, I think, is a good candidate. So imagine, as I mentioned, this idea of a concept that then is reused, but in a more abstract setting. So imagine you have images and text, you're learning from all of that, but then you move from the concept from the domain of objects to more abstract concepts, and you want to keep some of those concepts, such as larger than and smaller than and so on, and reuse them. Of course, there's a need for applications, and in there, the goal is to really apply the NSI cycle, the NeuroSymbolic integration cycle, at scale. And I think healthcare is the most obvious application there, but more generally, AI accountability, and maybe in finance, there are some interesting applications of the idea of combining knowledge and data. So these are some of the references that I mentioned, and some other references that I regard as relevant, starting from the 1999 up to 2023. But of course, there are many more, and as you do this, there's always a risk of keeping a lot of relevant work out. But these are the ones I managed to cite in this talk. And so with that, I'll thank you, and happy to answer any questions if there are any.
Thank you very much, Artur. Very, very engaging and interesting talk. Maybe because we are short in time, maybe just pose one question and you can address others later. So you mentioned killer apps for NeuroSymbolic AI and the healthcare domain is one space, and the financial institutes. Do you have any thoughts why maybe it took so long to come up with such propositions, right? Typically, we all agree that there are many deficiencies in let's say state-of-the-art AI, or definitely machine learning, and typically the need precedes the solution. And here I would not say that we have a solution, but we all work towards that. So I don't know if you have any comments as for why we are not.
Thanks for that. So Yeah, one of the things that we've been trying over the years with let's say the workshop and some other meetings and events was to bring the community together, and I think this was the main issue, right? We have been AI has been in two different communities with different data sets. So it was very early. It was very difficult early on to have that kind of acceptance in the different communities, because the data sets were geared towards either symbolic approaches or exclusively towards neural networks. And I think now we are seeing that there is a clear need for combining. In the case of healthcare, you do have text. Everything is handed over in terms of text, and then you also, of course, you also have images. So the multimodality aspect. And now we have some benchmark data sets looking at multimodality and looking at those the right data sets where you can ask these questions. And of course, we have also the risks of ChatGPT and what we are seeing there as highlighting the need for reasoning and so on. So I think we are finally in the right direction when it comes to real applications.
Wonderful. So thank you very much, Artur,